Uh, we were studying fluid mechanics up until this point, but now we are going to go into a similar process called heat transfer, the basics of which we have introduced in previous classes. We all know we are going to restrict ourselves in the first part of this course to conduction transfer process, conduction heat transfer. In what we have seen is the major equation which defines the thermophysical property, thermal conductivity, is Fourier's first law of conduction. There we have seen is that the heat flux is proportional to the temperature gradient and the proportionality constant is K, the thermal conductivity, and we have also seen that Q should be equal to minus K dt dx or Q double prime. The minus sign signifies that the heat travels from high temperature to low temperature. One of the major objectives of conduction heat transfer is to find out the temperature distribution in a solid as a result of the changes that are taking place in its boundaries. Apart from that, there may be a situation in which heat may be generated inside the system as well, the combined result of which is a change in temperature, maybe with time, maybe with position inside the solid object. What we will try to develop today is some equation which would give us the temperature inside the solid as a function of its position as well as its function of time. So, but then again we are not going to deal with transient heat transfer. In my part of the course, transient processes will be handled by Professor De. So, I will restrict myself to steady state heat transfer in different geometries utilizing the heat diffusion equation. Now, in order to develop the heat diffusion equation, what we are going to do is, again we are not going to go for all the steps, rather we will only highlight the important steps. If you think of heat diffusion equation, it is nothing but a statement of conservation of energy. So, if you think of a cube of size dx, dy, dz, then through the x face which has area dy, dz, some heat may come in, some heat flux may come in through the face at x plus delta x. We will assume that q x plus delta x would be leaving the system. Same for y and y plus delta y face, z and z plus delta z face. We may also have a situation in which there would be some amount of heat generation in the system. So, in minus out plus generation should be equal to the amount of energy or rate of change of energy stored in the system. So, that is nothing but conservation statement. In minus out plus generation or minus depletion should be equal to rate of amount stored in the system. So, that is the concept based on which we are going to derive our heat diffusion equation. And what we will also going to do is, if Qx is the heat flux at x, then the heat flux at x plus delta x can be obtained by making a Taylor series expansion of Qx, neglecting all the higher order terms. So, that means Qx plus delta x should be equal to Qx plus del Qx del x multiplied by dx. That is Taylor series expansion neglecting all the higher order terms. Same thing is going to apply for y phase and for z phase. We will also assume that, let us say, E dot g is the amount of energy generated per unit volume. So, we will have to multiply it with the proper volume and make all these in minus out plus E dot g multiplied by its volume, which is del x, del y, del z, should be equal to amount stored. Now, how do you sense that the amount stored inside a solid, the energy stored inside the solid is changing? What is the manifestation of that? Temperature change. So, in what is, if suppose T is its temperature, what is the energy storage in the system? If T is the temperature of a solid object, what is the energy stored? It is rho Cp, or rather m Cp delta T. So, that delta T could be any like T of the substrate which you are talking about minus some reference temperature. So, when I think of rate of energy storage, it should be del T, T being the time, of m Cp delta T, which is T of the object minus T reference, and that reference is a constant temperature. So that it's very simple. Then I am going to start with this cube, where I have Qx coming into the system, Qx plus dx going out. So Qx plus dx would simply be equal to, by a Taylor series expansion, same would apply for Qy plus dy and Qz plus dz. Okay. And if E dot G is the energy generated per unit volume of the system, then the total amount of energy generated would be simply E dot G multiplied by dx dy dz. So now if you think of in minus out plus generation is equal to the rate of change, that is time rate of change of energy stored, that's the basic equation. So I am going to have for in Qx and for out Qx plus del Qx del x times dx. So if I make in minus out, I am simply going to have minus del Qx del x times dx minus del Qy So this, I guess this step is clear to all of you. So what I have, the first three terms is, first three terms are the result of in minus out. This term is the generation term, and on the right hand side I have the energy storage. So that's straightforward. Is there any question up to this point? Okay. As I said, my primary aim was to find out the temperature distribution inside such a solid object, but I have these Qx, the heat coming in through x, heat coming in through y and through z. So how can I express these Qx's in temperature terms? What would be the next step? Fourier's law. These Qx can simply be expressed as minus k dt dx in this case multiplied by the area, and what that area would be? Dy dz. Okay, so that's the area, that's going to be dy dz. So I am simply going to substitute Qx is minus k times a, which is dy dz times dt dx. Same for y and same for Qz. So one, is it clear? So I am simply used Fourier's first law. So if I substitute this one in the previous expression which we have obtained by simply making an energy balance, the final result would be so this expression which is simply obtained by substituting Fourier's law for Qx, Qy, Qz is known as heat diffusion equation. Now can anyone tell me why it is diffusion? Why the name diffusion? I can understand heat, but why heat diffusion equation?
Because of the gradient, it's an outcome of temperature gradient.
All right, can you amplify a bit more, like why it is diffusion and I could simply say it's heat equation.
A region of low energy.
Pardon me?
Select the mass diffusion equation, the equation has a similar form. So fluid is not flowing necessarily.
Pardon me?
So fluid is not flowing necessarily. The body is
Okay. So what you're trying to say, maybe you're not finding the right word, is that the conduction transfer is a diffusive process. It does not require the movement of the medium, as you have pointed out. At the same time, it's a result of temperature gradient only, and obviously it also has the same form as mass diffusion. The important thing is to understand is that the conduction is a molecular level process. Okay. So, one molecule gets excited, it transports the or transfers its energy, excess energy to the adjoining atom and so on. That way the heat moves from one point to another as a result of difference in temperature. So, that is why it is more akin to that of a diffusion process, where the transport is by molecular mechanism. So, that is why this is known as heat diffusion equation. Okay. So, this is the most general form of conductive heat transfer inside a solid object, and similar to this one, which is in Cartesian coordinate, I can also have the same expression for cylindrical coordinates and for spherical coordinates, which are given in your text. I am not going to go into the derivation of that. So, transformation of coordinates would give rise to slightly different form of this equation, but the basic concept would still remain the same, that it is going to be in minus out plus generation is equal to the rate of energy storage or rate of change of energy storage in the system. All right. So, we can see several simplifications possible of this equation. The first one is I can take k outside, and it would simply be times k times del 2 t del x square plus del 2 t del y square plus z. I can make this one. So, what are the assumptions that I have made in this? K independent of x, y, z, that means its position, and anything else, any other assumption that I have made? In order to write this equation from its previous form, you correctly identified that k is independent of x, y, z. Any other assumption that I have made? Can there be a situation in which kx, ky, kz are different? Or if I say that k in all directions is the same, what property of the material that I am talking about? Isotropic. So, the second one is it is an isotropic medium. So, such that the property, thermophysical property k is independent of its orientation. Some of the other simplifications which are possible is straightforward. For example, if you do not have heat generation in the system, the fourth term on your left hand side would be 0, and if it is a steady state system, then the right hand side would be simply equal to 0. Right. So, and if it is a case of one dimensional conduction process, then the governing equation would simply be k d2 t dx square is equal to 0. Okay. So, this is for 1D conduction with no heat generation and steady state. Right. So, at steady state with no heat generation in a plane wall, this would be the governing equation for temperature for heat transfer, and by solving this equation with known boundary conditions, you would be able to find out what is the temperature distribution inside the solid object. Right. So, we are going to for cylindrical and spherical systems, as I said, other equations are, the equations have slightly different form, which you should be able to find out from your text. Once I have this form of the equation or any form of the equation, I still need certain boundary conditions to solve this problem. So, to solve the to find out the temperature distribution. Now, many of these I have already discussed before, but I will very quickly go through some of them. The first boundary condition that you can think of is temperature specified. So, that means at any location, at any specific location, the temperature may be known to you. So, that could be one boundary condition, the most obvious boundary condition which you can use. The second one is constant heat flux. So, how are you going to express constant heat flux if you know that one wall of this room is experiencing or is getting 5000 watt per meter square of energy from somewhere. So, how do you express that? Okay. So, you are going to simply use Fourier's law, k times dt dx at some location x equal to x1 is equal to q double prime s. That means the surface heat flux q double prime s is a constant and is known to you. So, it has to be connected with the temperature gradient at that location using Fourier's law. So, that is another kind which again we have discussed before. The third one is adiabatic or insulated surface. So, if it is an adiabatic or insulated surface, what would be the form? Heat flux is 0. So, q double prime s at that location would be 0, which would simply give you dt dx at specific location is equal to 0. And the third one is known as convection boundary condition. So, that means whatever be the heat that is coming to one surface by a conduction process is being taken up by a convection process at the boundary. So, if you have a solid wall and it is generating some amount of heat and the solid wall is exposed to an air stream, at steady state the amount of heat produced in the system or amount of heat which is coming to the surface must be equal, amount of conductive heat must be equal to the convective heat transfer from its side. So, minus k dt dx at that specific location should be equal to h times T of the surface minus T infinity. So, the form of that would be so this part, as we spoke about many times, this is Newton's law of cooling. This H which defines, which is an engineering parameter for convection process, is the convective heat transfer coefficient. So, the amount of conductive heat coming to a specific location must be equal to the convective heat which is going out, and I think we spoke about the boundary layer which forms near the solid surface, and we emphasize that these boundary layers are generally very thin, and you can increase H by increasing the turbulence on this side. That's one way of increasing the H, but whenever you increase H by turbulence, you require certain excess energy to be spent for making that process more turbulent. So, there has to be a balance, engineering balance at some point. How much turbulence would you require to, I mean, you have to basically consider what's the cost involved for the imposition of turbulence and the gain that you are having by increasing the value of H. So, that's a completely separate subject about optimizing H in terms of cost and ease of operation, which we will discuss later on. But these are the four common boundary conditions which you will experience in conductive heat transfer. So, with that we are now going to go into starting with the simplest possible case, in which I have, let us say, T1 and T2 being the temperature at two sides of a wall. We would like to find out what is the temperature distribution. You all know about this, so I do not think that I do not want to spend too much time on this. This simply follows from this would be my governing equation. Starting with this governing equation, you obtain the heat flow or the heat flux, which would simply be T1 minus T2 by L, and since d2t dx square is 0, it also tells us that the profile is going to be a straight line, and the amount of heat that travels from one side to another side is simply going to depend on what's its thermal conductivity, what's the temperature gradient, and so on. This is straightforward, you have seen it before many times. Now, let us say I have another surface where the temperature is, let us say, T3. Okay. I have some heat which is Q double prime X coming in here, and this sort of a profile I am going to get. Which key is larger? This is K1, this is K2. Which has larger K? K1 is large. Okay. So, since the same amount of heat is traveling through this, so since the temperature gradient over here, so this is at steady state, this is also going to be Q double prime X. So, it simply tells you, if you write K1 for this and equal to K2 for T2 minus T3, and if the two L1 and L2 are the same, then you can obviously see that K1 is going to be large. So, large thermal conductivity means smaller temperature drop. Okay. Is it clear? Fine. Now, when we look at this expression, I can write the total equation as that means, say, instead of flux, if I write the total amount that gets transferred for surface A is K of surface A times T2 minus T1 by delta XA, where delta XA is the thickness of the plate in the X direction. Now, which is cause and which is effect here? In between Q and everything else, which is the cause? Temperature difference, not T, it is the temperature difference which is the cause. This is the effect. So, cause and effect are generally related by what? If you think of Ohm's law. Okay, and the proportionality constant is some sort of a resistance. So, if I like to express it in that form only, so this Q is equivalent to what in Ohm's law? It is the effect. Okay, so this has to be the current, all right, and this would be my voltage, all right. So, this should be my resistance. So, similar to the resistance in electrical conduction, I can simply write this as T2 minus T1 delta XA by L by KA. So, this whole thing is my resistance. So, the resistance to conduction, okay, resistance to conduction is simply equal to delta XA, that means the thickness of the wall, thickness of the layer through which conduction is taking place, divided by KAA, K of that material multiplied by the area. This is resistance to conduction. If instead of one such wall, you have 10 such or 5 such walls, what is going to be the form of this equation? You can derive it, but let us see your intuition. So, she is saying that it should be final temperature minus initial temperature divided by the sum. Is this sum of all resistance? Okay, sum of all resistances. So, if I write the Q for a multi-layered wall, it is simply going to be equal to T initial, because that contains a minus sign in front. So, I am changing it to T initial minus T final divided by the sum of all resistances. Okay. And the sum of all resistance would simply be equal to delta XA by K of A multiplied by A plus delta XB K of B and so on. All right. So, that is clear. So, that means that if you have a multi-layered system of different materials of different thicknesses, then using the continuity of heat flux, that means the same heat moves through all of them at steady state, you can see that these resistances are simply going to be in series. So that's the whole that's the outcome of this thing. So it's going to be the heat flow is going to be the potential difference divided by the sum of all resistances. Any question? If you have a system in which you have conduction and convection combined, so I have a wall, one side of which is exposed to a hot air stream, the other side is exposed to a cold air stream with the convective heat transfer coefficients H1 and H2 on both sides. T infinity 1 is the temperature far from the wall, T infinity 2 is the temperature on this side, again far from the wall, and we know approximately that it's going to be a thin boundary layer. The temperature at this location is Ts1 and at the other location is Ts2 at x equal to L. And I would like to find out like what kind of equation, what kind of this Ohm's law sort of equation I can write for this case. How many resistances do I have? 3. Are they in series? Okay, they are in series. So what is the we know the conductive heat transfer resistance is going to be delta x, which is in this case is L by Ka. What is the convective heat transfer coefficient? Convective resistance to heat transfer? 1 by H or 1 by HA if I write it in terms of the total amount. So I have 1 by H1A, 1 by H2A and L by Ka, all these in series. So this is going to be my total resistance. So total resistance for convection conduction combined system is going to be my convective heat transfer on one side, convective on the other side, and this is the conductive on conductive resistance for the wall itself. Now sometimes what happens is that instead of writing these three resistances, when you have especially a number of resistances, an overall resistance is defined. So in that case this Qx is U times A delta T overall. So in this case U is nothing but an inverse of resistance, alright. This U, which is known as the overall convective heat transfer coefficient. Overall heat transfer coefficient, this overall heat transfer coefficient is nothing but an inverse of the sum of resistances. So what in this specific case, what's going to be the expression for U?
1 by H1 plus 1 by H2. So 1 by plus 1 by K.
1 divided by the total R, summation of R. So this is going to be 1 divided by the summation of R, and we already know what R is. So this U, you are going to see this the presence of these U later on in many of your engineering calculations. So keep in mind that this U is called the overall heat transfer coefficient. Pardon me? Okay. How does it help? Yes, it apparently for this type of Cartesian system, it's obviously of no use. I mean, I know it's going to be R, so why bring in another U which is simply 1 by R, nothing else. Now let's think of a cylindrical system, alright. Now if you think of a cylindrical system, let's think of a thick pipe, the inside of which is exposed to a convection environment, the outside is also a convection environment, and you have some amount of conduction resistance due to the thickness of the pipe itself. Now you can define two different U's. Is it possible? I can define two U's for that system when I have a thick pipe with inside and outside convection at inside and outside. Is it possible? How the conduction in cylindrical or spherical system is different from conduction in planar systems?
R varies continuously.
Only one direction system.
Now, I am talking only, I am restricting myself to one dimensional conduction only. Okay. So, what did you say, like what is different?
So R varies.
R changes, R changes true, but more correct term, area changes. So, the cross sectional area changes. Now, let us think of a situation in which I have this, let us say this is the pipe. So, over here I have some convective resistance, here also I have some convection resistance. Now, the total amount of heat which flows can be expressed as using our convention of convective overall resistance UA. Now, should there be any subscript to UA for a cylindrical system? What U are you talking about? A is different for each of them. So, I should be able to express something based on internal area. I can also write this to be equal to outside area. So, whenever you think of systems in which your surface area changes, then you can have two different types of U's, overall convective resistances, based on inside area or based on outside area. But no matter what, your UI AI should be equal to U0 A0. Okay. So, you can see that for planar these kind of systems, you have to define some sort of standardized resistances. So, since your resistances, since your these things are going to vary, so it's customary to express overall heat transfer coefficient based on either internal area of the pipe or external area of the pipe. And all the engineering calculations, all the monographs that you have would give you some value of U as a result of what is happening inside, as a result of what kind of thickness of the pipe you are using for your exchange equipment, and that's why U's are important. Okay. Instead of knowing all these resistances individually, you have an estimate of what is going to be the overall resistance. So, that is why U's are, you would be able to find out what are those values of those convection resistances, overall convection resistances, instead of knowing all the details of the resistances. And you only have to know is whether it is expressed in terms of the internal area of the pipe or external of the area of the pipe. Then you can do your first, at least your initial preliminary calculations without knowing the details of the system, which is very important in engineering, and that is the use of overall convective heat transfer resistances. All right. Now, so we know that these overall heat transfer resistances, and there are certain things which are only an extension of what you have studied in electrical technology. For example, you may have a number of walls connected to each other, and some of the walls could be in series, some may be in parallel as well. For example, you may have a system in which these are more of academic interest, I would say, that you have a wall where heat is coming in, a different wall, but this is insulated, or I would say this is an adiabatic surface, and then you are going to have the heat outside. So, you have resistance 1, 2, 3 and 4. Now, what would be the circuit diagram for this? Okay. So, 2 and 3 are parallel and these are in series. Okay. So, this kind of simple geometrical things you would be able to know. I do not need to spend any time on that. Okay. What we should spend some time rather is what is going to happen in radial systems, because as you have correctly identified is that the radial systems are different because there you have change in surface area, change in conduction area as you move in r direction. Now, so let us see what is going to happen. We have a cylindrical system, all right. So, the two radii are r0 and ri, specifying the inner radius and outer radius, and let us say the length of this is L. It is a steady state one dimensional conduction in the r direction. So, I can simply take the heat diffusion equation in cylindrical coordinate, cancel out del T del x and del T del theta terms, right. It is only del T del r which is going to be important. So, theta and z direction terms, the variation of theta with z and with the variation of t with z and theta terms can be neglected. There is no heat generation and it is a steady state case. So, in the heat diffusion equation for cylindrical coordinates, the only term which would remain which contains del T del r. Is it clear? I do not need to write it, I suppose. Okay. All right. So, that equation for cylindrical systems is this one. For a one dimensional case without any heat generation, this would be the form of the equation. All right. So, you can simply find the temperature distribution in let us say the two temperatures are also known in this case. This is T0 R0 and Ti Ri, and you can see it is a logarithmic distribution, and once you solve it, which I am not going to do, is this would be the temperature distribution. So, instead of a straight line case, you are going to get a logarithmic distribution of temperature. You simply find out C1 and C2 using these two boundary conditions, and this one would result, which I skipped. Any question apart from the steps which you can figure out? Fine. Now, if this is the temperature distribution, what you can also find out is, using Fourier's law, you can find out the heat QR, the radial heat. Should I repeat anything here?
So is that R2 or not R1?
This is,
ln R by R.
it should be RO then. So, now I can evaluate what is the heat that is going passing through each of these different R planes. Now, if you think, you have correctly identified that the surface area keeps on changing. If the surface area keeps on changing, will the heat flux be constant or heat rate will be constant? I repeat my statement again. We have identified that the surface area available for conduction as we move radially outward changes, increases. So, in that case, would my heat rate be a constant or heat flux be a constant? Heat rate. Someone saying heat rate. Why heat rate? Okay. And why not heat? Why heat flux?
Same heat is going out through a different area, but coming in through a different area.
So, which one is going to be constant, rate or flux? Rate is going to be a constant, yes. The heat rate is going to be a constant, because if you simply apply the conservation one, whatever comes in has to go out. If you have any accumulation or any unbalanced one, then you are going to have a change in temperature, which cannot happen at steady state. So, always keep in mind that in planar system, both the flux and the rate are constant, whereas in cylindrical or spherical systems, the rate is a constant, but not the flux. Okay. And this would give rise to a very interesting situation, which we will discuss later on. So, the flux will never be a constant. So, I can write using Fourier's law from here what is the value of dt dr. From here I can find out what is dt dr, and that dt dr can now be multiplied, and you can see that if I write dt dr from here, I am going to get an 1 by r because of the logarithmic, because of the presence of the ln term. So, dt dr would be something multiplied by 1 by r, okay. And when you multiply this with the proper surface area, what you get is twice. Again, I skipped few steps in here which are not necessary for the understanding of the process. So, the heat rate, which is a constant, is going to be, the expression of that is going to be this. So, what is conductive resistance for one dimensional conduction? Conductive resistance in cylindrical system. In planar system, you have found out it is going to be L by Ka. So, in this case, the resistance is going to be ln R0 by Ri by twice by Kl. Okay, so that is going to be the resistance. So, resistance for cylindrical systems is simply going to be logarithmic of ln of R0 and Ri divided by twice by Kl. So, if you have a large such systems of cylindrical things, one after the other, what is going to be the resistance? Are they, it's going to be still, it's going to be summation. But give me an example in which practical example in which you have a large number of such things connected in series. An example where, why should we study this at all? First of all, give me an example of a planar system in which you may have a number of such things connected. Anything that comes to your mind? Anything that you see in this room where it is going to be a planar system with multi-layered, the wall that you see here. Okay, so probably this one is something different, a plaster of Paris or something. Then you have a layer of brick, maybe some cement, and on the other side you have a paint which is a third surface. So, whenever in heat transfer, whenever you would like to reduce the heat losses or heat gain of a system, you use multi-layered coatings. Okay. So, if it is a pipe carrying steam, you would like to insulate it such that it is going to lose the minimum amount of heat. So, in that case you would put some sort of an insulation on the outside. So, that is an example of a cylindrical system having more than one wall, and the walls can be of different material. So, in that case also it is going to be in series, but the heat that you are going to get Q radial system is going to be T infinity 1 minus T infinity 2. The T infinity 1 and T infinity 2 are the two temperatures inside the pipe. This is T infinity 1, and you then have a number of such ones, and this is your T infinity 2. So, you are going to have convection, first resistance is convection, and the last resistance is also convection, and in between you have a number of conductive resistances, the same way we have drawn for the planar system. So, what is going to happen, what is going to be the first resistance? If let us say the inner one has a radius equal to R1 and the convection coefficient is H1. So, what would be my first resistance? 1 by H1A, and what is A in this case? 2 pi R1 into L, if L is the length of this pipe, times H1. What is going to be my second resistance, where I have, let us say this is R2 and this is R1, this resistance is R2, ln R2 by R1 divided by twice pi K of material A times L. Clear? That is the resistance form. Then I am going to have similarly ln R3 by R2 2 twice pi kbl, and finally I am going to have the outside resistance, what is 1 by 2 pi r4, I am sorry, r3 in this case, LH2. Am I right? Yes. Okay. So that's what going to be a number of such systems based on convection, convection, and a number of conduction resistances in between. Now, this Q I can also express, as we have done before, by UA delta T. All right. Now, this delta T is obviously equal to T infinity 1 minus T infinity 2, and this brings us back to the discussion that we were having. For cylindrical system, the expression for U or the value for U would depend on which A you are choosing. If you are choosing the inside area, then this is simply going to be twice pi r1 L. If you are choosing the outside area, it is going to be twice pi r3 L in this case. So, depending on which area you choose, and the two common areas which are chosen is either the inside area of the pipe or the outside area of the pipe, and depending on that you have either UI, convective heat transfer resistance based on the inside area, or convective heat transfer resistance based on the outside area. Okay. No matter which you choose, you are simply going to get slightly different form of the expression and nothing else. Is that part clear? Okay. Then in the next one, what we are going to do is it's very interesting. I think I have introduced it to you in some of my discussion. What we will see mathematically how it works. Let's say I have one pipe which has radius Ri and temperature Ti, and this pipe is insulated by some material, and this is R0. The pipe is exposed to a convection environment of H and T infinity. So, a bare pipe, okay, some sort of insulation over here, and this circular, so it is insulation around a circular pipe, and inner temperature of the insulation is fixed as Ti, and the outer surface is exposed to a convection environment. My question is to you is what would happen if instead of R0 as my insulation, I make it 2R0. This one is hot, it is losing some amount of heat to the atmosphere. So, in order to reduce the amount of heat that this pipe is losing to the atmosphere, I have put the insulation around it. So, what would happen if I increase my thickness of the insulation? Let me repeat the question. Let us say I have this as a pipe, and it is hot, its temperature is 100 degrees centigrade. So, in order to maintain it at 100 degrees centigrade, what I would do is I would put an insulation around it. So, putting the insulation increases the resistance for heat flow from the pipe to the ambient, where the temperature, where the convection coefficient is H. Now, when I do that, if instead of one such insulation, I put another insulation around it, can you say anything about the amount of heat that is lost from the pipe to the surrounding? Would it be less, equal? Okay. So, our common sense tells us that if I put an insulation around an object, the heat loss or gain of that body decreases. So, instead of one sweater, if you put two sweaters during the winter, you feel more warm. That is a common situation. But can there be a case in which by adding insulation, you will be adding, you will be helping heat transfer from the object? So, that is the case, and this is what we are going to call as critical thickness of insulation. So, if this is the case in which the insulation thermal conductivity is K, the amount of heat lost from the pipe to the outside is simply going to be delta T divided by the sum of resistances. One resistance is a convective resistance, which we know what it's 1 by HA. The other resistance is conductive resistance. Now, this R0 somewhat shows what's the insulation thickness, and we would like to find out, is there a situation in which Q is going to be a maximum for some R, or rather R0. That means I am trying to find out, is there a way, is there a situation in which Q is going to be maximum. That means the heat loss from this pipe through the insulation to the surrounding, can it be maximized for some specific thickness of insulation? Initially, what we are tempted to think is that if I remove the insulation, that is a situation in which my heat flux is going to be maximum, isn't it? I have a shirt on, and then I take off that shirt, then obviously I am going to feel more cold. That's the usual perception. But can it be can this be a case that I have a shirt, I put on another shirt, and I feel even more cooler? Is there a specific insulation thickness which would maximize my heat transfer even when the insulation is present? And mathematically, the only way to do is, if I find out dq by dr0, put it equal to 0 and see what is the condition that I would get. So, if you do dq dr0 is 0, what you are simply going to get is, everything else remaining constant, then you have something in the denominator as well. You do not have to write it, you just see what we are going to get at. If I now my R0 is a variable here. So, if I make dq dr0 is equal to 0, I get this sort of a form, and this simply tells you, to make it equal to 0, your R0 should be equal to K by H. Mathematically, this is what it is giving me. But what is the physical significance of that? That is much more important. So, the result simply tells us that as long as your R0 is less than this value, you are going to increase heat loss from the pipe by adding insulation, contrary to our expectations. When you cross R0 equal to K by H, this value, whatever be that value, suppose this value is equal to 10, suppose 10 some unit. So, as long as your R0, that's insulation thickness, is less than 10, you increase heat loss by adding insulation. Once you cross that value of R0, your heat flux or heat loss is going to follow what you expect. That means, by adding insulation, you decrease the value, decrease the amount of heat transfer. Now, this thickness, this specific thickness, which depends on the material property of the system, material property of the insulation, and what is happening, the flow property, what is happening on the outside of the insulation. It is simply K of the insulation divided by H, the convective environment your pipe is exposed to. This is known as the critical thickness of insulation. So, that means, if your thickness is, again, if your thickness is less than the critical thickness of insulation, by adding insulation you increase heat loss. If it is more, then by adding insulation you get what is expected, you have less heat transfer. But why would this happen? Now, let us just to give you an idea, like what would this value be. This K for insulating material is generally of the order of 0.03 watt per meter Kelvin, and H is roughly of the order of 10 watt per meter square Kelvin. So, which simply tells you that this R0 is going to be of the order of 3 millimeter only. Okay. So, if your value of, if you are dealing only with very thin wires, the concept of critical thickness of insulation is of any relevance, because if you in engineering systems, with the physical system that we always deal with our body, we never come across, we never deal with 3 millimeter pipes. Okay. So, in 3 millimeter, if you so that is why when you put two sweaters, we always feel warm, because our critical thickness of insulation is definitely much more than this 3 millimeter, roughly the 3 millimeter limit that we are imposing on it. But there would be a system, so that is why in most of the engineering systems you never come across critical insulation of thickness, but you have to appreciate that there exists something like that. And why would that happen? By adding more insulation, we are increasing the conductive resistance, but at the same time we are increasing the surface area, right. So, we are increasing the conductive resistance, but decreasing the which one? Convective resistance. Okay. Because you provide more surface for convective losses. So, you increase your conductive resistance by adding more insulation, definitely yes, but you are also decreasing your convective resistance by adding more surface. Okay. So, instead of one of these, if I put another cap, I definitely increase my convective area, the area available for convection, and the total resistance to heat transfer is a sum of these two, the conduction resistance and convection resistance. Conduction is a monotonically increasing function. You add more insulation, your conduction resistance increases, but convection is slightly different. The sum total of these two, as a result of which, passes through a minimum. The sum total of these two resistances passes through a minimum, and that is the point where you get maximum amount of heat transfer. And so, it is a direct result of the concept of the fact that in radial systems as well as in spherical system, your area changes, your convection area or your area changes as you move in R. So, your critical thickness of insulation is a direct result of that. It is a very interesting example. The only application I could think of is in the case of electrical wires. They could be less than 3 millimeter in thickness, and you would probably like to have more heat loss by adding an insulation. You have to add an insulation, electrical insulation on a wire, and by adding that insulation you are helping in heat transfer, which is what you want, because you do not want your wire to be very hot. So, what you do is you add electrical insulation, that in turn increases heat transfer. So, your system remains cool. So, apart from that, I do not think there is any other application where this is going to be of use. The only other example which is possible is when you wear contact lens. Your eye is a spherical system, you add an insulation contact lens which is nothing but an insulation. Okay. So, there may be a situation that your eye will lose more heat during winter when you have contact lens on compared to the system when you do not have contact lens. So, this critical insulation of thickness is important concept, since it gives us an idea, a quantitative idea of how the convection resistance changes, and at the same time its applications are limited, but sometimes very interesting.